know. I really thought I hit that record button. Oh. Hello, little voice. Okay, number 20? Was that the one?
Yeah.
Yeah. Okay.
You move the decimal, right?
Right.
At however many exponents.
Yes, whatever the exponent is, you move it that many.
I did that and it said it was wrong.
Okay. If I look at this one, we've got 9.9 times 10 to the third. So my decimal point is here. I'm going to move it 3 places. Gives me 9, 9, and I have 2 zeros to fill in. So this should be 9,900.
Can I give you the question that I got? And
Sure.
Can you walk me through that one? Okay, so mine was 5.8 times 10 to the 7th.
So I'm going to do 5.8, go 7 places. 1, 2, 3, 4, 5, 6, 7.
How do you know?
Go ahead.
How do you know which way to go over? Like if you go left or right?
All right. I tried to explain this last time. I'm not good with left and right. I'm that person who gets my sense of right and wrong. And so if the exponent is positive, I should end up with a big number.
Okay.
And so I'm going to move it so I have a big number. If my exponent is negative, it'll go in the other direction because that'll give me a tiny decimal.
Okay.
And so now I've got 6 zeros to fill in. So that gives me 58 million.
Okay, thank you.
Welcome.
Can you go over number 30?
Sure. And folks, my intention is to start every class by asking if there are homework problems. And if I don't, it's because I forgot. Please ask me if you have homework problems at the beginning of class. All right, perform the indicated operation, write the answer in scientific notation. So perform the indicated operation, whoops, I have 6.9 times 10 to the 6th over 7 times 10 to the 4th.
I remember with the induction, they didn't get intense until my water broke.
Who's ever talking about their labor, could you mute yourself until you have a math question? Thank you. I'm sorry, it's 6.3. So 6.3 divided by 7 is 0.9 times 10 to the 6th divided by 10 to the 4th. When I subtract, I get 10 to the 2nd. Moving over 2 places, that gives me 90. Then to put it back in scientific notation, that would be 9.0 times 10 to the 1st. Technically, this is not scientific notation. It's not your final answer, because in scientific notation, you need 1 digit in front of the decimal. Better?
Yes, thank you.
Welcome.
Can you go over like the last 3?
Last 3, then 19. And
Thank
then we're
you.
starting with the new notes.
Yeah, I think we should be good after that one.
30.
I'll look at mine and see if I had any other questions on problems before we end this session.
And when you're doing your homework, if you have this many questions, please do me a favor. Question help. Ask my instructor. I could have gotten back to you over the weekend if you would have done that, all right? So we've got 2x to the negative 8, y, z to the negative 9 times 2x to the negative 5. Order of operations, there's nothing to do inside the parentheses. Exponents, both things in that parentheses is being raised to the power. So that gives me 2 to the negative 5, x to the negative 5. With me so far? Now multiplying, I add exponents. 1 plus -5 gives me 2 to the -4. -8 plus -5 gives me x to the -13. Y and z can belong to the right. Get rid of the negative exponents. Anything with a negative exponent, that factor becomes positive when it moves to the denominator. Anything with a positive exponent will stay in the numerator. And then lastly, 2 to the 4th, when all is said and done, is the number 16. Yes, no, maybe.
Yes.
Yeah.
Thank you.
Next, more of the same, except here with this one, first thing that we have to do is raise everything inside the, no, actually, I lied. Got carried away for a minute. We've got x to the 4th, y to the 3rd, z to the 5th, over x to the -4th, y to the -3rd, z to the -5, all being raised to the -2nd. Starting inside the parentheses, I can simplify this because I can divide by subtracting exponents. 4 minus -4 is 8. 3 minus -3 is 6. 5 minus -5 is 10. Now when I raise that to the -2nd power, when I raise a power to a power, I multiply those exponents. Then to write with positive exponents, I'm going to turn it into a fraction. Factors with a negative exponent, it becomes positive when they move to the denominator. And if there's nothing left, the numerator is 1.
I have a question.
Sure.
How did you get the x to the 8? Did you combine the x to the 4th and x to the -4th somehow?
Remember when you divide, if I have x to the m over x to the n, when you divide, you subtract exponents.
Yeah.
I'm doing what's inside the parentheses first. Inside the parentheses, I need to do that division. And when I do that division, I subtract my exponents.
Thank you.
Better?
Yeah, it's good. Thank you.
Okay. Next one too, or are we gotta roll with these?
I have one last question.
Sure.
When you see like the two things like times each other, like you have like x to the 4th times like x to the 5th, like what do you do with exponent? Like how do you get an answer out of those? Because I don't really understand the exponent rules. So do you think you can touch on that real
X
quick,
to the
please?
4th times x to the 5th. This means I have 4 x's. With
Yeah.
me so far? This means I have 5 x's. So how many x's do I have altogether?
You have 9, but I didn't know if you would multiply the exponents too or just
You add
add
them.
them.
If you've got the
Now,
same
does
base
it
that you're
change the-
multiplying, you add the exponents. Instead, if I
What if
had x to the 4 to the 2nd, that would mean that I have x to the 4th twice, which would give me x to the 8th. So when I raise it to a power, I multiply exponents.
Okay, but when you're just multiplying them by themselves, it's just you add them.
Right.
And does that change ever, or is it always just add them?
If you're multiplying same base, you add the exponents, always. We'll rewrite those rules before we begin today.
Okay, thank you.
And then before we got involved with these last ones, somebody asked about number 19. Do we
Yeah.
still need to look at 19?
Yeah.
Oh, 19's an easy one. What makes 19 easy is we got all this work to do inside the parentheses, right?
Yeah.
But what power are we raising it to?
0.
0. And everything in here is being raised to the 0 power? Anything to the 0 power is 1.
Oh, okay. Thank you.
Okay?
Yeah.
Better?
Yep.
Yep. If you were a glutton for punishment, you could simplify what's inside. 6 divided by 12 is a half. A to the -2 over a to the 2 would be subtracting a to the -4. B to the 4 minus negative 3 would be b to the 7th. But when I raise that to the 0 power, everything inside gets raised to the 0 power. And anything to the 0 power is 1, so that product would all just be 1. Okay? Oh dear. Can you guys hear that in the background? My neighbor is practicing her trumpet.
Oh no.
It's
Oh, no.
beautiful music.
Yeah, it's
You know
beautiful.
what? Two of my children from 4th grade to they got out of high school played the trombone. That was challenging like the first year. I remember my son being he must have been like 8 years old, running around the house, chasing the dog with a trombone, doing elephant blasts.
I used to play the trombone.
I used to play the trombone.
Yeah, it's a cool instrument, and they eventually got really good at it. But those
And the-
first couple
I
of
play the
years, it was
piccolo, too.
challenging. Say it again?
I play the piccolo.
Ooh, that's the exact opposite. Teeny tiny and very
Play
high.
something for us, Lonnie.
Oh, I don't want to get it out and interrupt class time.
Yes, thank you. Not during class time. So,
Maybe
okay.
maybe after class.
All right.
Okay.
Okay, let's first remember our rules for exponents. And the first deal with if you have a common base. If I have x to the m times x to the n, if I'm multiplying and the bases are the same, I add the exponents. If I have x to the m over x to the n, if the bases are the same and I'm dividing, I subtract exponents. Subtracting exponents can give us an exponent of 0, which gives us 1. Subtracting exponents can give us a negative exponent, which means take the reciprocal. If I have something raised to a power and I raise it to another power, that's when I multiply those exponents. If I have only multiplication inside parentheses, everything in the parentheses gets raised to that power. We will find later if there's an operation other than multiplication or division in there, that does not hold. If I were adding and subtracting, that would not hold. But multiplying and dividing, anything that's in that parentheses will get raised to that power. And those are our exponent rules.
Can you leave that up for a second so I can finish writing it all down?
Sure, or if you want to, these will get posted in Blackboard and you can get them then.
I'm writing the last one right
And if
now.
I remember correctly, last class we ended, well, just before we end it, we put this information up there. So it is in the notes already. And is everybody all right? If you are not in class, you can still get the notes that you missed because the written word is posted in Blackboard. And as long as, thank you for whomever reminded me, as long as somebody reminds me to hit the record button, there's a YouTube video of the class. So you can still sit through class if you want to. And I guess, I don't know, when I have to sit through a YouTube video, I speed it up so that it doesn't take as long to listen. Isn't that awful for me to admit? All right, are we good?
Yeah, I think.
Okay.
Yeah.
Then we ended up last class talking about radicals. And we had said if I have something like the square root of 49, the square root of 49 written like that is 7 because 7 squared is 49. Technically, there are two roots of positive and negative. If I want the negative one, I'll put the negative sign out in front. And if I want both, I'll put that plus minus sign out in front to get 7 or negative 7, the two different possibilities. We also said that if I take the square root of something squared, it will always give me the absolute value of that quantity. So for example, if I take the square root of -9 squared, while squaring and square roots undo each other, order of operations, first thing I do is square what's on the inside, which gives me a positive 81. And because there's no minus sign out front, that becomes positive 9. So it's like taking the absolute value.
If we get a plus or minus radical, how do we know which one we're going to pick and which is the right answer?
If there's a plus or minus, you need both of them.
You need both of them?
Yes, if there's a
'Cause
plus or minus, you need both of them. I think in my math lab, if there's more than one answer, they ask you to put a comma in between them.
Okay. I learned at like some point in my math career that we would have to reject one of those. Will we ever have to do that in this class? Like
The only
reject?
time you're going to necessarily reject something is if it's a word problem and it does not make sense, or when you do a check, it does not work. You don't automatically reject one unless if it's something like an absolute value problem or a radical equation. You'll reject numbers that are outside of the domain that don't make sense, that don't check. If it's a rational, a fractional problem, you'll reject numbers that give you a 0 in the denominator because that doesn't make sense. If it's a word problem, sometimes with word problems, you're going to reject something that gives you a negative result because we're not going to talk about negative time or negative distance. Otherwise, don't immediately assume you're going to reject something because it's negative.
Okay, thank you.
Now,
And I apologize.
don't apologize. I appreciate that you're care enough to ask. So now let's look at something like the square root of, let's say, -4. Is there something that I can square and get -4 as its answer? If I square 2, I get 4. If I square -2, it gives me +4. So this is not possible. And so for a while, we're going to say that they do not exist. It's not real. We will find later in the semester that there are numbers that are not real. We'll use our imaginations then. So you cannot take the square root We'll find later today that there are some roots that we can take, but you cannot take the square root of a negative radicand. So outside of that, saying that you can't have a negative under the radical, that a lot of what we just said was a quick review from last class. We're going to go on now and look at the way we had rules for exponents. We're going to have some rules for radicals. And whenever I write that rules for radicals, it brings me back to a point in my life where I was a community organizer, and that was a title of a book for organizing. But no, I don't mean Alinsky's rules for radicals. I'm not telling everybody to go out and march. I'm looking at rules for radical expressions. And
Did you always want to be a math teacher?
No, at one point in time, I wanted to be a community organizer and change the world.
Oh, that's
So,
cool.
And I always wanted to be a mom. I kind of think that that mom was the most important job I ever did.
That's fun.
First rule is the product rule. And if I take the square root of A times the square root of B, that's going to equal the square root of A times B. And that's a two-way street. So that rule could also be written as the square root of a times the square root of b, pardon me, is equal to the square root of a times the square root of b. Other rule we have is a quotient rule. And it says that the square root of a over b is equal to the square root of a over the square root of b. Or the other way, the square root of a divided by the square root of b is equal to the square root of a over b. They're two-way streets. They work both ways. So if we look at some straightforward examples that just apply those, can I scroll up?
No, I needed. Oh, I'll just get them from the things later. Well, can I just take a picture of it real quick and then write it down as you're
Sure.
going?
Or again, they are
Thank you.
posted later. Is this penmanship neat enough, guys?
Yeah, it's perfect.
So let's look at a few examples. If I have the square root of 3 times the square root of 27, working this way, well, that's the square root of 3 times 27, which is the square root of 81, which would be 9. Thank you. Instead, if I have the square root of 32 times the square root of 2, I can think of that as the square root of 32 times 2, which would be the square root of 64, which is 8. Likewise, if I had the square root of 20 over the square root of 5, I can think of that as the square root of 20 over 5. And 20 divided by 5 is?
5. No.
4.
And the square root of 4 is 2. So these rules make sense.
Yeah.
We're going to use these rules, though, to help us put an expression in simplest form. And we're going to say that a radical is in simplest form if there's 3 criteria we have to meet. First one is that the radicand has no perfect square factors. Second one, the radicand is not a fraction. And the third one is that a rational expression, so that's a fraction, cannot have a radical in the denominator. And I know for you folks, because your generation, you're probably most used to, if you're trying to find the square root of something or trying to evaluate or simplify something with a square root symbol, and you take out your calculator and do whatever computation you can. These rules kind of go back to ancient times when I was a kid and we had to do it all by hand. And so it was much easier to simplify a radical and look up the square roots of smaller numbers in a table to find a root by hand than it was to go through the long algorithm with large numbers. If you look at a square root in the denominator of a fraction, it became ugly division. If the square root was in the numerator of the fraction, it wasn't quite as ugly. But whatever the origin of these rules, although back in ancient times it made computation easier, they still apply. When I look at trying to put a radical in simplest form, I personally find it, I'm going to turn the page because I want to write something kind of long out. I personally find it easiest if I start with a list of my perfect squares. And if you have this list of perfect squares on the side of your paper, it makes simplifying easier. So what do I mean by that? What's 1 squared?
1, 1,
1. 2 squared is
2,
6.
6,
Two.
4,
4.
4,
2 times 2 is 4. Let's try that again. 3 squared, 3 times 3 is
9.
9,
4 squared is
8.
5 squared is
25.
25. 6 squared is
36.
7 squared is
49.
8 squared is
4.
9 squared is
81.
10 squared is
100.
11 squared
110.
121.
121. 12 squared
yeah, Blondie.
Thank you.
144.
144. 13 squared
169.
169. And I've run out of room, but you can keep that list going. And we're going to
Yeah.
use those to help us simplify a radical. What we're going to do first, and let's look at an example as we do this. Let's simplify the square root of 18. This one's pretty simple. First thing we want to do is we want to find the largest perfect square factor. So, factor of the radicand. So here my radicand is 18. Which of these perfect square numbers goes into 18 evenly?
Four.
9.
9. 18 is 9 times 2. Then we use the product rule. So I can think of that as the square root of 9 times the square root of 2 and simplify what we can. The square root of 9 is 3, and so my final answer is 3 square roots of 2. I know some people kind of like to jump right from here to here. I know it's a lot of writing in between, but if you write it out, you're less likely to make a careless mistake.
So that equation wouldn't be 3 times 1?
No, it's 3 times the square root of 2.
Okay.
Can you
But
do
that's
another
Square root
example?
the square root of 2 is something like 1.41, and I forget the rest of it.
Oh, okay.
Okay. Next example. What if I have the square root of 75? Which of those perfect square numbers goes into 75 evenly?
5.
Well, 25? 3
Yeah.
times. So then when I take the square root of 25 and multiply it by the square root of 3, my final answer is 5 square roots of 3. Next one, we're going to find there's a couple ways of doing it depending on whether you see the answer is the glass is half empty or half full. Excuse me. If I have the square root of 32. From the right-hand side of this column, which is the largest of these numbers that goes into 32 evenly? If you can't find the largest, can anybody think of any perfect square that goes into 32 evenly?
Is it 4 or 8?
We can think of that as 4 times 8. So we can think of that as the square root of 4 times the square root of 8, which would give me 2 square roots of 8. But if we're going this way, we're not done yet. Because is there anything that goes into 8 evenly?
4 and
2?
2. So that becomes 2 times the square root of 4 times the square root of 2. Or 2 times the square root of 2. Or 4 square roots of 2. Which is a fine way of getting there. However, if you can get to the point where you see 32 instead as 16 times 2, if I would have used 16, it would have taken me to the 4 radical 2 a little bit more quickly. They get interesting when you start throwing variables in there. If I have the square root of x to the 6th, what would I square in order to get x to the 6th? Something squared has to equal x to the 6th. But when I raise a power to a power, don't I multiply those exponents? So that would be x to the 3rd. Be careful. In my math lab, if they don't accept the x to the 3rd, sometimes, and it's not consistent, but sometimes I want you to put absolute value bars around it. Actually, if it's not exponent, they'll ask for absolute value bars. And so if I wanted the square root of 9x to the 8th, I'm going to think of that as the square root of 9 times the square root of x to the 8th. The square root of 9 is 3. The square root of x to the 8th would be x to the 4th.
4th, yep.
Is everybody all right? This time I don't need absolute value bars because an even exponent is always positive.
Wait, where do you get the x to the 4th?
When I take the root, for the square root, you half the exponent. And it goes back to the idea that if I'm squaring, I double the exponent.
Oh, okay.
Okay? So let's try to fit one more on here. What if I have the square root of 300x to the 10th? Let's look at that 300. Is there a number that goes into 300 evenly that's a perfect square?
100.
So I'm going to think of that as 100 times 3 times x to the 10th. So we'll take the square root of 100. We'll take the square root of 3. We'll take the square root of x to the 10th. The square root of 100 is 10. The square root of 3 is the square root of 3. So the square root of x to the 10th would be x to the 5th. Here, bad penmanship. Can you picture somebody who drew that too long and all of a sudden you're wondering, is the x to the 5th under or not? And so it's most normal to write things that are not underneath the radical in front. And again, because that 5 is an odd exponent, I think that in my math lab, if they don't like it written that way, put that x to the 5th an absolute value. I'm going to turn the page and look at another one that's a little different. What if I have the square root of 25x to the 7th? Because that's an odd exponent, it's not a perfect square. So what we're going to do is we're going to take one factor away. We'll take one factor out. So we're going to change that into the square root of 25x to the 6th times x. Is everybody comfortable with the idea that x to the 6th times x to the 1st would give me x to the 7th? And now, because x to the 6th is even, we can take its root. The square root of 25 would be 5. The square root of x to the 6th would be x to the 3rd. And then that extra one has to stay under the square root symbol.
So you can separate them and under the radical to make it more simplified?
Yes, you have to, like we did here. As long as they all multiply to the same thing. So let's look at one that's a little bit more involved. If I have the square root of 72 x to the 4th y to the 9th. Not everything under there is a perfect square. 72 is not a perfect square, but is there a number that goes evenly into 72 that is? Well, let's see.
Does 9 go into some of these too?
Yeah, but if I go bigger, I think 36 does.
Okay.
Okay? X to the 4th, it's even, it is a perfect square. Y to the 9th is not even, it's not a perfect square. So we'll change that into y to the 8th times y. Now, I look at this and it reminds me of a whole bunch of kids trying to share a party hat. Never works. So I'm going to give them each their own little hat. And then the square root of 36 is 6. 2 is not a perfect square. It has to stay in. The square root of x to the 4th is x to the 2nd. The square root of y to the 8th is y to the 4th. And that other y has to stay in. Then I'm going to rearrange everything outside of the radical gets multiplied. And the 2 left in the radical get multiplied underneath. I think that's as bad as they're going to look in this section for you folks. So why do we want to simplify radical expressions? Because the next place we're going,
Is that a Z?
where,
Oh no, it's 2, right? 2y.
yeah, it's a 2.
Okay.
If there's a line in the middle, it's a Z. If there's no line in the middle, it's a 2.
Okay, thank you.
Because we're going to try to add and subtract radical expressions. And just like addition, and we can only add like terms, you can only add like radicals. And like radicals are going to have the same radicands, same thing underneath, in the same root. And we'll find later the idea of the same root is going to be referred to as the index. So for example, if I have 7 square roots of 5 plus 9 square roots of 5, do you see how the radical parts are the same? They're like. And so just like combining like terms, I'm going to undistribute. I'm going to add the coefficients. And so my final answer would be 16 radical 5. Instead, another example. If I have 10 radical 7x minus 6 radical 7x, are the radicals parts the same?
The inside, yeah, the inside's the same.
Inside's the same, so it's going to stay the same. And then outside, 10 minus 6 would give me 4. Another example. What if I have 2 radical 3 plus radical 2 plus 5 radical 3? Oh boy.
You can
Yeah.
combine the first one and the third one because they have the same radicand.
So that gives me 7 radical 3. And that other one, because it's not like, we're going to just leave it at the back.
I have a question.
Sure.
Later on in like the semester, will we learn how to change the base and stuff as well of radicands or no?
What do you mean by change the base?
Like to change like the radicand at all, or can you change the radicand in the equation if it's like 3? Can you change it to a different number?
No.
Somehow? No.
The only way you can change them is like this next example. So I think you're reading my mind a little bit. If I have the square root of 75 plus the square root of 48, the way those are written, can I add them?
No.
No, because they're not like. The only way I can change them is if I can simplify them. So let's first look at 75. Is there something that goes into 75 that's a perfect square?
25.
So that's 25 times 3. So I can simplify it to the square root of 25 times the square root of 3, or 5 square roots of 3. So I guess in one way we changed the radicand, but we did it by simplifying. Now, how about 48? Does anybody know anything that goes into 48 evenly? You
12?
guys want my cheater's way of looking at it?
6.
Can I give you my cheater's way of looking at it?
Of course.
Yeah.
In order to combine, we're hoping 3 goes in there. So I'm going to try 3 first. How many times does 3 go into 48?
16.
16. Oh, and look at there. That's a perfect square, so it's going to work. So now that I've simplified them, can I add them?
Yes.
And my final answer is 9 radical 3.
9
And shoot, I wanted to get a lot further than this today. That next homework, I'm going to push back from being due Wednesday, the one due Wednesday, to being due Friday. Might not get there till later on the day, but I do promise I'll make those changes because we haven't finished the section yet. But let's look at one more example. Let's look at 3 radical 8 minus radical 32 plus 3 radical 72 minus radical 75. Right now, I can't combine any of them, huh?
No, you can't.
But we can simplify. So let's see, what should we do with that square root of 8? What goes into 8 evenly?
4.
4. And so that gives me 3 times 2 times radical 2, or 6 radical 2. What goes into 32 evenly?
6.
8.
8.
8.
But that's 8 times 4. I think we can go bigger. Does 2 go
32 times 1.
16.
16 times 2? And so the square root of 16 is 4. And so that's 4 square roots of 2. Now, what goes into 17? And again, these two guys had 2. Does 2 go into 17?
36 and 2. Okay.
And is 36 a perfect square?
Yes.
So I like it. So that's 3 times 6 times the square root of 2, or 18 square roots of 2. And how about 75? I don't think 2 goes in there, but
Definitely not 2.
I think we just did that.
25.
25 times 3, so that's 5 square roots of 3. Now, is everybody all right? These ones are like. So 6 minus 4 is 2 plus 18 is 20 radical 2. And then that last one is not like, so we can't combine them. And so this would be my final answer simplified. And by my phone, we've just got a minute left. So I'm going to stop there, even though part of me really wishes we went further. Are you guys all right? Am I going too slow, too fast? Okay.
I mean, I'm good if you want to do like another 15 minutes. I'm sure everyone else would be fine with that too.
Except I have another class in 15 minutes that I have to get ready for.
Then we can go another 10.
So,
They can wait. We're more important.
I just want to do more math today. I want to learn more.
okay, well, I think we're going to just call it a break here because where we're going next, well, let's see. Has anybody seen fractional exponents?
Yes.
If I were to write 16 to the 1/2 power, does anybody know what? Oh, wait, no. That's not where we're going next. We're rationalizing denominators and we're going to leave that. So we're going to just stop here. All right? So,
Aww.
But what that means is that homework that is due on the 16th, I will push back so that it won't be due until the 18th. All right?
Are you gonna stay on with me so we can figure out the email
Yes,
thing?
I am.
Okay.
So let me stop recording. Is there anybody who, whoops,